so I set quite a few chemical problems in that podcast. Let's have a look at the solutions. The first one resolved around quinine. This is the structure of quinine, and I asked you to work out the molecular formula of quinine from the structure. So the first thing we need to do is to count up the carbon atoms. Well, we have one carbon atom here. We have 6 carbon atoms in this benzene ring. We have 1, 2, 3 remaining carbon atoms in this pyridine type ring. Then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbon atoms in the remaining framework. So in terms of carbon atoms, that should give us C, 16, 19, 20 carbon atoms. We then have to count the hydrogen atoms. Hydrogen atoms, of course, are always more difficult to count because we don't see them on the structure. We have 3 hydrogen atoms on here. I'll note it down. We have 1, 2, 3 hydrogen atoms on here. We have 1, 2 hydrogen atoms on here. But notice we don't have a hydrogen atom here because it's already bonded to 4 different things. We have 1 hydrogen here. There are 3 bonds going into this carbon, so the 4th bond must be to a hydrogen. Again, 1, 2, 3, we need a hydrogen here. 1, 2 bonds to this carbon, so 2 hydrogens here. Similarly, 2 hydrogens here, 2 hydrogens here, 2 up here. There's 3 bonds into this carbon, so 1 hydrogen here, 3 bonds to this carbon, 1 hydrogen here, 3 bonds to this carbon, 1 hydrogen here, and only 2 bonds, the double bond here to this carbon, so there are 2 remaining hydrogens on here. So if we tot up the numbers, 3, 6, 8, 9, 10, 11, 12, 13, 15, 17, 19, 20, 21, 22, 24 hydrogen atoms on quinine. We then count the nitrogens, of which there are 1, 2. We then count the hydrogens, the oxygen atoms, of which there are 1, 2. And there we have the molecular formula of quinine, C20, H24, N2, O2. We can use this to calculate the molecular mass of quinine as follows. If there are 20 carbon atoms, that's 20 times 12, the atomic mass of carbon, that gives us a mass of 240. There are 24 hydrogens times 1 equals 24. There are 2 nitrogens, each of which has a mass of 14. That gives us 28. And there are 2 oxygens, each with a mass of 16. That gives us 32. And therefore, the overall mass is 4 carry 1, 5, 6, 8, 2, 1 to carry. 324 is the RMM of quinine. And the final thing I asked you about quinine was, is it chiral? Well, if we focus in on this part of the molecule, where we've drawn in 3 dimensions, of course, for something to be chiral, we need to have groups pointing in different directions. We need 4 different groups on one carbon atom. If we have 4 different groups on a carbon atom, then the mirror image is non-superimposable. If we look at this carbon atom, we have an aromatic ring, we have another ring with a nitrogen in it, we have an OH group, and our 4th group on here is a hydrogen, which must be pointing backwards if the OH was pointing forwards, and therefore this atom in quinine is a chiral centre. Is it the only chiral centre? There's an extension problem for you. Go away, have a look at it and think, are there other chiral centres in this structure of quinine? So let's solve those other problems that we're looking at. First of all, we considered pinene, and we're going to look at the molecular formula of pinene. It's the same kind of problem as what we already looked at with quinine. First of all, we have to count the carbon atoms. We have 1, 2, 3, 4, 5, 6, 7 around the basic framework. 8 is here, 9 and 10 are here and here. That gives us 10. We then have to count the hydrogens. That's a little bit harder. Remember, the hydrogens are hidden, so there's 1 bond to this carbon atom here. The remaining 3 must be hydrogens. This carbon already has 1, 2, 3, 4 bonds, therefore no hydrogens attached. This carbon, 3 bonds, therefore 1 hydrogen, 2 hydrogens on here, 1, 2, 3, 1 hydrogen on here, 2 hydrogens on here, 1 hydrogen on here. If we come to this carbon, it has 4 bonds, so no hydrogens. These 2 groups are CH3s, so we have 3 on each. That gives us 3, 4, 5, 8, 11, 13, 14, 16. C10H16 is the molecular formula of alpha-pinene that gives these juniper berries their fragrance. And then we can consider the citric acid problem. I said draw it in skeletal form. Here it is with all the atoms showing, and it's a bit of a mess. We can kind of not very clearly see the functional groups. Much better to draw out a carbon skeleton. And so what we do is we draw a zigzag chain for the carbon skeleton. So we have 5 carbons in the longest chain here. So we'll draw a 5 carbon zigzag chain out on the board. On the left hand end we have a double bond to an oxygen and an OH. On the right hand end we have a double bond to an oxygen and an OH. And on this central carbon we have an OH attached, and we have a carboxylic acid attached on the 1, 2, 3rd carbon along the chain. Just rub out that form from above, and we can see very clearly the structure of citric acid. 3 carboxylic acid groups, 1 alcohol, and they jump straight out at us when we draw the structure in this form. You may be thinking, is this a chiral structure at this point? Does it have 4 different groups attached to this carbon? Well, the answer is no. This side and this side are symmetric. Therefore, we don't need to show these with wedges and dashes in 3 dimensions as we normally would for different functionalities on these kind of groups. The final problem I set you was the structure of the key component in the gin and tonic, the ethanol component. And of course, ethanol has an ethyl group and an alcohol attached, and if we drew it in skeletal form with the zigzag chain for the carbons, there's CH3, CH2, OH, ethanol. And so that's it. Gin and tonic. We have the tonic, we have the juniper berries, we have the citric acid from the lime, and we have the ethanol from the gin. And it's the molecules that make the drink so good.